Hello, I'm Jan Kotek and I would like to give you an introduction to my hobby project, which is a Java database engine with some interesting features and incredible performance. This project has been around for last 12 years. You may know it under name JDBM, which is a Java Database Manager. And last year at the version 4, we decided to do complete rewrite and rename the project. This project is just entering alpha phase, which means that most of the features are actually implemented, but we still have some issues like concurrency issues, data corruption and some other stuff. So you can download it from the GitHub, test it, but it's not production ready yet. So MapDB is a database just like others, but it provides Java collections instead of some proprietary API. It means you can take map, set, list or queue or other interface provided in other implementation provided by MapDB, insert inside billions of records or half terabyte of data, and because it's backed by disk storage, you will never run out of the memory. You can also use 64-bit you can also use 64 gigabytes of RAM without dealing with garbage collection and other Java related stuff. MapDB is fully concurrent. It means that we are using lock-free data structures or data structures with minimal locking. Also, MapDB uses asynchronous serialization and disk writes on the background thread, so you can actually take advantage of the concurrency even if your application is single-threaded. MapDB has incredible performance comparable to native DB. It's a pure Java, but we have very interesting performance optimization techniques, which I will explain later. It's our goal is to replace or provide alternative to projects like LevelDB and others. MapDB has some very interesting features usually found in the bigger databases like MVCC, snapshot, transaction journals, ACID, and basically the development is moving at the incredible speed and new features are adding every week. For example, tonight I decided to add append-only storage, log-based append-only storage, and after 3 hours it's nearly finished. I'll have to do some testing and hopefully we'll submit it next tomorrow or very soon. MapDB also integrates some stuff usually found in the ORM object relation mapping frameworks, such as serialization and instance cache. We found that this type of stuff is important to have in the database because it minimizes some overheads like serialization overhead, and when it's tightly integrated in the database, it can really improve performance. So let's go to the hello world. As you probably know, every database claims that it's very simple to use, but I think MapDB takes the simplicity of use to the next level. This line actually opens database. That's all you need. What it takes is that it creates some files in temporary directory and creates database inside. Then it opens the database as map, and it's a standard map, so you can insert stuff inside or take it out, use iterators, value set, key set, and all the usual stuff. So this will actually open temporary database which is discarded after the JVM shuts down. This is a more complicated example. It actually opens durable database which is persisted between JVM shutdowns. There is DBA file. There is MapDB uses a builder style interface. So first you specify what type of storage you want, if in memory, file, or some kind of transactional creation. Then you specify some additional options using builder interface. In this case, we want to close JVM on the shutdown using shutdown hook and enable encryption. and then you call make, which will take all the options and actually opens the database. The database interface is in here, and then you can take database and get a named collection in the fashion similar to SQL tables. So in the MapDB, the collections are actually used similar way as tables in the SQL. So this is the continuation of the previous example. We put some stuff in the map and then call commit. As you can see, the changes are persisted. We can add some more stuff. Now it's 1, 2, 3, and we call the rollback, and in this case the MapDB will revert to the last successful commit, which was 1, 2, and at the end we can close it. I really try to make this stuff as simple as possible, so I hope I was successful. So MapDB has two goals. First is simplicity. It means that MapDB should be very simple and easy to use, and it should be also very simple and easy to modify and grasp and hack around. This misconception, or most people think that simplicity equals to minimalism. This is not actually true. MapDB can be very feature rich, but we achieve the feature richness by combining a few basic principles. I am not sure if you are familiar with Git, where you have basically each commit is just stored as modification of the previous commit, and it's linked together in the linked list, and all the revisions and all the branches and everything is just kind of linked list view in the same way. MapDB tries to be simple in this way, but be feature rich by combining simple features. So next stuff in the simplicity is that MapDB is implemented as set of components which are separated through the uniform but simple way, and you can take those components such as encryption and asynchronous serialization or instance cache and stack them on top of each other, so you can basically mix and match the feature set you want. I will explain this a little bit later. And last but not least, it's very easy to hack and modify or design criteria that basically anyone should be capable of modifying or adding new features in the MapDB in just single evening. So if you take MapDB from GitHub, open it, in one evening you should be able to add some logging or exceptions tracing and stuff like that. And it's related to the simple algorithms we decide to use. There are some very clever concurrency algorithms, but we are actually trying to avoid those because they may be kind of hard to grasp and hard to modify and test. So to put it simple, MapDB is very hackable. It's not black box. You can take it, and if you run out of the configuration options to optimize your application, you can actually modify MapDB to fit your goals. It's very simple to implement new instance cache or new compression algorithms and stuff like that. The next goal, and the second and only goal, is the minimal overhead. MapDB was originally developed as a storage engine for the astronomical database application, and we were trying to replace programs which are actually written for 486 CPUs, which are very slow, and I was always getting complaints that my program is slow and the competing programs runs much faster on the 486 and stuff like that, so I kept optimizing until I reached MapDB. It has some interesting side effects. For example, MapDB doesn't really, or the developers do not really care about the performance. Until recently, we didn't even have performance benchmarks. We simply were more interested in the profiler output and minimizing minimizing the code overhead. Rather than optimizing for the maximum performance, we minimize the overhead. So the performance is just really a side effect of this type of optimization. The bad side of this is that some code in MapDB is very compact, and it's maybe more similar to C rather than Java. For example, we try to avoid recursion and object allocations and stuff like that. But really nice about MapDB is that it really has minimal overhead. It can run just fine with 16 megabytes of heap, and it never throws. It has minimal garbage collection. It has minimal impact on garbage collection, and it never throws out of memory exception. One important feature which sets MapDB apart from any other database written in Java and probably in C++ and other is that it doesn't use binary arrays to pass around. Usually you have a database API and you put inside binary data, and excuse me, and then you get binary data back when you execute some type of query. In MapDB you pass inside the database object instance with serialization, with serializer, which converts the object instance to the binary data. But DB itself, or MapDB itself, is in charge of when this data are serialized and in what thread it is done. So this allows us very interesting performance optimization techniques like instance cache, asynchronous serialization, or for example, you can take the data and serialize them, send them over the network, and store them somewhere completely else. The nice about this is that you can use the same uniform interface. We call it engine for serialization, for binary storage, or for the object instance cache. We simply have single interface which is called engine, and it's used for the 99% of the features inside the MapDB, like encryption or instance cache. For example, encryption is just engine which swaps the serializer and applies transformation on the serializer and then pass it in the wrapped engine. So the other interesting feature is that MapDB is record oriented. It's not official term, but it explains how MapDB is different from the other databases. Other databases usually have fixed size page, and the page size is actually one of the biggest configuration option in most databases. If you use 32 kilobyte blocks or 512 byte long blocks and this type of stuff, MapDB doesn't has this. It just has a bunch of records with different sizes, and there's no page size, no page cache, nothing like this. This caching is actually controlled directly by your operating system, and if you want to enable more, if you want to give more RAM or stuff like that, you have to go and tune it in the operating system. Nice thing about this is that there is minimal overhead or minimal layers of abstraction between the disk and objects which are and objects themselves, and also the class the B3 nodes and hash buckets and dir buckets and stuff like that are represented by Java classes, not by binary data stored in some kind of blob. So first, now we are getting to the indexes supported by MapDB. The most advanced data structure in MapDB is 3map, also actually called the B3 map inside the sources. It's a classical B-linked 3 by described by Lehman and IO about 20 years ago. It's used in many databases, including H2, Berkeley DB, sorry, not Berkeley DB, Derby, Apache Derby, and others. It's very classical structures. In MapDB, we just optimize it a little bit. And the nice thing about this structure, it's fully concurrent. It doesn't require much locking. When the reads are completely lock-free, and when you are updating it, you only have to lock one single node at a time. So the concurrent updates on this type of structure are really fast. Also, it's very similar to the classical B3, and if you know B3s, you will probably find it relatively simple to understand this collection. The major difference between B3 and B-Link 3 is that the B-Link 3 stores links between the nodes, and when you are inserting or updating the node, the data structure itself or the tree structure never gets corrupted. So data can always can be found, and you don't have to lock for the reads. Only the updates needs to be locked to prevent concurrent updates. But so it's very fast with concurrent updates and concurrent reads. The tree map inside the B3 map actually implements the concurrent navigable map from Java 1.6. There are only two implementation I know about. First one is the skip list map or concurrent skip list map inside the Java collection, Java concurrent collection, and second implementation is in the MapDB itself. The B3 map supports some interesting features like delta K compression to minimize the space used by minimize space consumed by binary data stored on disk. Also, you can specify the node size, and you can also specify where the values of the tree tree map will be stored inside the nodes, outside of the nodes, or you can store them in the completely separate storage engine. Second collection is used inside the B3 inside the map. MapDB is hash map. It is implemented as H3 map. The major difference between hash table and hash tree is that hash tree kind of expands when the collision happens. In the hash table, when you find hash collision, you have to expand the table and move the data around. This is not necessary in the H3. So nice thing about this is that's a very predictable performance, and it's very fast. H3s are used in the Linux XT file system. I think in XT4 are enabled by default, so you can bet that it's very fast very fast structure. In the MapDB, the default settings are optimized for the large keys, as opposite of tree map or B3 map, which is optimized for small keys. So we actually have two index structures inside the MapDB, but because they are optimized different way, they actually complement each other. We also have sets, which is tree set and hash set. It's basically just map without values. There is no magic about it. We have queues. Right now we are trying to implement lock-free first in, first out, and last in, first out queues. It's under development, so I hope to finish it in a couple of weeks. You can check it on the GitHub if you are interested. And now the serialization. MapDB itself is actually very efficient serialization framework, which you can use outside of the database as well. The goal is to provide space efficient and fast serialization. So we believe that minimizing disk space used by data maximizes the performance. It also goes with our goal to minimize overhead, and by minimizing the disk space use, we minimize the overhead. So first case is that MapDB implements special serializers for Java util and Java lang classes. So for example, booleans and some integers are serialized only with only single byte. It's called byte header. It's basically one of the 255 values is reserved for true, false, and stuff like that. Other cases, for example, some longs. Yeah, in this case, 4, 5, 6 is represented. It only takes 3 bytes because the first byte indicates the data type, and it's followed by a packed long, which only takes 2 bytes, and so on. Basically, MapDB serialization is very efficient when it's used for the Java util or Java lang classes. Then we have a generic POJO serialization. The major difference from others is that it tries to mimic Java serialization. So you actually have to implement Java lang serializable interface, marker interface, to make your classes serializable. We are also implementing externalization and some other stuff you found in the Java serialization. The major difference is that from Java serialization is that MapDB doesn't store the class structure with the record, but it stores it in the separate place, in the single centralized place in this data store. So if you insert, I don't know, 10,000 persons inside the database, the class structure of the class person is not stored 10,000 times, but only single time. You can see it in this example when you have a class person, and because Java serialization stores all the information as class name and field names and stuff like that, it's serialized the stuff using 105 bytes, as opposite of MapDB, which also uses 105 bytes, but those 90 bytes are stored only once in the single space, so you actually have overhead of only 15 bytes per record. This POJO serialization is enabled by default, and you will be if you insert person into database, you will be using it without even knowing that. For example, Berkeley DB Java Edition has something similar, but it takes some configuration to actually implement it to start using it correctly. In MapDB, it's enabled by default, and it's very transparent. Okay, we can continue. MapDB provides instance cache, as I said. Its instance cache is actually one of the reasons why MapDB is so fast. It reduces the serialization overhead, and if you have enough RAM, it means that your data model can fit inside or your data can fit inside the memory. Thanks to the cache, the database will be nearly as fast as in-memory data model. The instance cache actually blurs division between heap and disk storage. In the MapDB, it's very hard to tell if the data you are fetching are inside the cache or inside the disk storage, because the transition between cache and disk storage is invisible, or it's very small. And one of the criteria for instance cache is that they should have nearly zero overhead, and so we use very simple and easy to optimize algorithms for instance caches. So the default is the hash table, which is bounded, and it uses fixed size hash table, and if there is hash collision, the new item simply removes the old one. It's very simple and nearly zero overhead cache. The second option is the least recently used cache, which is concurrent, and it has some interesting features. You can see it in the source code if you want. It's also fixed sized, and in some cases it can have better performance, but because it keeps history of the items in which they were inserted, it has a little bit higher overhead than hash table cache, which is on by default. If you have enough memory, you can use soft or weak reference cache. The problem with these is that they usually introduce high GC overhead, as garbage collector is trying to keep track of all the references, and if you simply insert few millions or hundreds of millions items in the cache, it kind of becomes slow. If you have enough memory, the probably best is hard reference cache. We found that it will be too hard, or it will have too big overhead to keep track of the items which are in the cache, which are not. So we implemented simple solution where we simply monitor the free memory or free heap memory, and when it goes under 25%, we simply drop the cache. It becomes thanks to the fast serialization, the cache becomes populated very quickly. So it's very simple and efficient way how to prevent garbage collector from trashing. Okay, now we are in the write modes. MapDB has right now two modes, or two durability modes. Well, there are many options, but two most important. In the first mode, which is called direct, the changes are written directly in the file. So it's very in the file buffer, and because they are written directly, and some changes may arrive later than the others, it's very easy for a file to become corrupted. So in this case, it's very important to close database after you are done correctly, otherwise you will lose data. But because MapDB is usually used as replacement for the Java collections, which are not durable, you lose your data after the JVM shutdowns, it's sometimes not really an issue. And also because this mode is using mapped memory, it's very fast. We got some really incredible performance number, which most people don't believe, but so you can test it yourself. I think you will be very surprised. Basically, this mode is designed for the maximum performance, and it trades durability for maximum performance. The second mode is journaled. Journal log. Basically, it writes all the modification in the log file, and when you call commit, all the modifications are replayed into the main storage. It's durable as any other database. It relies that file flush and file rename are correctly implemented by operating system, so it's not as stable as other databases which are using append only algorithms, but for example, it should be as stable as, for example, Apache Derby, or H2 database, and some others. In the case if database crashes, MapDB simply tries to replay the last good log found on the database startup. The interesting thing about this is, unlike most other databases, we are not using fixed size pages. We are actually using instructions. So if you modify single byte in the file, we actually write offset and that single byte, which is 9 bytes, rather than the entire page. So which is, I don't know, usually 4 kilobytes. So thanks to this, the write mode in the journal mode is actually quite fast, and it can beat up even other databases, even if they are memory based or stuff like that. The third mode we are currently working on is append only. So the data are appended at the end of the file, and on the commit it updates some flags, art markers that the commit happened. And the nice thing about it is it's a very robust way to store the files, and it's nearly impossible to corrupt it. When the database starts, the log is read completely, and some metadata like record offsets are replayed inside the memory. So it means that during the database restart can be, or database start can be quite slow, because you have to read and replay all the log. But it's sequential read, so it should be reasonably fast. This append only mode is currently not in the public repository. It's currently under development, and I hope to finish it soon. So we are getting to the interesting features. MapDB has snapshots. It's implemented in the other way than most of the databases, but because we are using maps and other collections, we need to implement snapshots in the way they will be actually useful. So I think we actually handled to implement them very well. So in this example we have concurrent map, which is modified concurrently, and we need to track the number of items in the map. So we simply take a read-only snapshot, which will conserve the map state at a certain time, and then traverse all the items in the map and get the size. In the MapDB, the size on the collection usually requires traversing the entire collection. We don't keep the track of the number of items in the collection because it will hurt concurrency. The nice thing about snapshot is that they are independent features, so you can decide that you want to drop everything else for the maximal performance, but you can still keep the snapshots. So you can have a non-durable write, you can have a non-durable write and asynchronous and stuff like that, but you can still use snapshots. MapDB, unlike most other databases, MapDB has atomic operations, which means atomic updates and atomic compare and swap updates. This type of stuff is found in SQL. It's actually built in the SQL, but it's quite unusual for the NoSQL databases to have this type of stuff. I think Redis is actually built around the idea of atomic updates on the limited collections. So first, MapDB has low-level atomic compare and swap operation on the record. So you can take, for example, B3 node and swap it for other by comparing the binary data and stuff like that. It can do some very interesting stuff. Then all the maps provided by MapDB are implementing concurrent map, which means you can take key value pair and swap it atomically by comparing value, and so you can atomically swap value by comparing with previous value, and if the previous value matches the expected value, it's just have a look at the concurrent map interface and how it should be used properly. I think this is described well in the Java documentation. For the MapDB, the CAS, compare and swap, is preferred way to deal with concurrency. It's because MapDB is more like alternative to the Java memory model rather than the database. I know it's kind of hard to explain, but we consider concurrent transactions and snapshots a little bit heavyweight, and if you want to squeeze the maximum performance out of MapDB, you should really consider atomic operations. Like in the Java 5, you can find atomic variables. It means that it's simple wrapper which uses atomic operations to modify and, for example, increment and swap and stuff like that to modify some values. For example, you can have a counter which is incrementing every time you call it, and it doesn't require a locking because it uses atomic operation to get an increment on value. So in this example, we use atomic long to get number of items or keep track. Sorry, in this example we use atomic long to generate unique UIDs. So if you are inserting new value in the tree, you are guaranteed that there will be no. Sorry, if you are inserting new key in the map, you are guaranteed that there will be no conflict, because each UID generated by this is smaller than or bigger than the previous one, and you have a guarantee that it's unique. The other interesting feature in the MapDB is collection binding. This is an alternative to the secondary maps or secondary indexes found in the SQL. So for example, if you have a relationship between the two tables and you want to keep them synchronized in some way, collection binding in binding in MapDB is the way to do it. So in this example we have two maps. First one is using some kind of unique ID and string, and it's primary, and the secondary map is using the same ID as the first map, and as value it's hold the length of the string in the first map. So for example, if you want to quickly calculate the number of strings which are smaller than certain size, you will use the secondary map, and the way to keep them synchronized is the collection binding. So you take the secondary value, or you call it secondary value, which is static method. You pass the primary secondary maps, and then you call some kind of transformation functions which takes the key and value in the first map and returns the value in the second map, and then the MapDB will just take care of keeping those two items synchronized. So if you put this value, this key and value in the MapDB in the primary map, the secondary map will contain the same key and the requested value, which is the length or size of the string in the size of the value in the first map, in the primary map. I know it's kind of hard to explain it, or but if you actually start using it, it's very simple and elegant way to keep your data model synchronized and have a secondary and primary indexes, and it can be quite powerful stuff for data modeling. The other collection binding is providing many utility methods. For example, in here we keep the track of the number of items inside the map. MapDB collections usually do not keep track of number of items inside the collection because it will hurt concurrency. So calling collection size typically requires traversing the entire collection, populating iterating all items in the collection. So you can use to keep track of the number of items, you can use separate variable which will be auto incremented and auto decremented every time you insert or remove stuff from the collection. In this example, we first get the map, the primary map, and the counter, which is secondary variable, and we bind it together. So every time you insert or remove stuff from the primary, which is a map, the secondary will get updated or incremented or decremented. This is a very nice example how certain features in the MapDB can be combined together to achieve new functionality or new unique stuff. MapDB has MVCC transactions. It means you can have multiple concurrent transactions. Each of them will see their own data they started with. It will not see the data which are it will not see the uncommitted data from the other database on other transactions. I think you can read about transaction isolation at the wiki. Basically, MapDB is implemented the hardest and most restrictive way. We believe that transactions are actually bad practice, and in the MapDB they are included only for the compatibility reasons. If you are, for example, migrating from other database which uses MVCC and you didn't migrate your data model to use atomic operations yet, you can use built-in databases in MVCC. The nice thing about the MVCC transactions in the MapDB is that they don't depend on the other features. So for example, you can have a non-durable direct mode, which is non-durable direct write mode, which is really fast, and you can commit I don't know, like 10,000 transactions per second on the disk-based. It's really mix and match the way you need it. Here's an example of how MVCC transactions are, how the concurrent transaction with MVCC isolation. Excuse me. So we can continue. So in this slide I will show an example of how multi-version concurrency control transaction can be used, or concurrent transaction with MVCC isolation can be used. First you open TXMaker, which is basically a transactional factory. Instead of calling make, you call make TXMaker, and then you basically pass block or transactional block, and this type of stuff is executed inside a transaction with full isolation and everything. If there is a conflict, the map will throw TX rollback exception, and TXMaker will simply roll back the transaction and try to execute this block again and again until it eventually succeeds. It's a very simple and effective way how to implement the transaction, but keep transactions, but keep the collections and all the interfaces simple. Here is the second example, or continuation of the previous example. The other way is to instantiate the transaction manually. So first you call TXMaker make TX, which is make transaction. Then you get some object from, then you instantiate the hash map from transaction, and you get some stuff, and then you have to close the transaction. Not closing the transaction is bad practice, because it will lead to the resources not being released, and you will eventually run out of the memory or disk space, depending how transactions are configured to store the data. I should probably explain that there is actually two types of transactions. In this example we are using transactions as well. So first MapDB has two type of transaction. One of them are single transaction per store, and the second type is MVCC, which are concurrent transactions per store. In most cases you will be probably needing only single transaction per store, and the way how to use it is the first hello world example. So in here we open the single database, and by calling make, and we simply we call db commit and db closed and stuff like that. In the last example we are actually using TXMaker instead of db, and we are using TXMaker to construct the transaction, which is in here represented by db. It's very elegant and simple way how to use multiple modes or multiple feature sets using single interface. MapDB has several other features like compression and encryption and other stuff. I may describe those later. Also MapDB is currently evolving, and we recently started performance optimization. So we don't have performance benchmarks yet, because the performance is improving every day, and publishing those in here will be basically made obsolete next week. But I would recommend you to check the websites if the performance benchmarks were recently published or not. You can also try MapDB on your own. I think you will be very surprised how fast Java can be. Okay, thank you for listening, and have a nice day.